Fox-Kemper. Thank you for taking the time to discuss your paper on mixed-layer instabilities. I have a few questions about the key findings and implications.
Of course, I'm happy to discuss the work. What would you like to know?
First, can you summarize the main objectives and conclusions of this study?
The main objectives of this paper were to investigate the dynamics of mixed-layer instabilities, MLIs, and develop a parameterization to represent their effects on frontal spin-down and restratification. Our key conclusions are: 1. MLIs rapidly bring the front to a balanced Richardson number of around 1 through a variety of instability processes. 2. The subsequent restratification by finite amplitude MLIs is insensitive to the details of the initial instability. 3. We derived scaling laws for the eddy buoyancy flux and residual diffusive flux that capture the essential dynamics of MLI-driven restratification.
That's helpful context. Can you elaborate on how the MLIs drive the restratification process?
Sure. The MLIs extract potential energy from the initial horizontal density gradient by slumping the isopycnals. This leads to an increase in the balanced Richardson number, which quantifies the relative importance of stratification and shear. As the Richardson number increases, the MLIs grow and transfer energy to larger scales through an inverse cascade. This restratification continues even as fronts develop, with the MLEs twisting and folding the front to prevent two-dimensional frontogenesis.
I see. And how does your parameterization capture this restratification process?
The key aspects of our parameterization are: 1. We use the vertical buoyancy flux, W'(B'), to directly relate the potential energy extracted to the restratification rather than relying on eddy kinetic energy arguments. 2. We scale the buoyancy flux based on the vertical length scale of the eddies, rather than the initial frontal width. This allows the parameterization to evolve as the eddies grow larger than the initial front. 3. We include a residual diffusive flux term that widens the front slightly, but is much smaller than the rest stratifying skew flux.
That makes sense. How do these parameterization approaches differ from previous work in this area?
Previous parameterizations, like those by Stone and Green, relied more heavily on linear instability theory and assumed the stratification remained fixed. Our approach avoids the limitations of the linear theory by using the actual eddy length scales and advective time scales observed in the simulations. We also explicitly account for the evolution of the front width as it is restratified.
Interesting. That seems like an important advancement. One final question. What are the key implications of this work for ocean modeling and understanding of submesoscale processes?
This parameterization provides a way to represent the effects of MLIs on frontal spin-down and restratification in coarse-resolution ocean models that cannot explicitly resolve these small-scale processes. More broadly, it highlights the importance of submesoscale dynamics in driving vertical transport and restratification in the mixed layer. Understanding and properly representing these submesoscale processes is crucial for accurately modeling mixed-layer depths, air-sea fluxes, and other key ocean phenomena.
Excellent. Thank you, Professor Fox-Kemper. This has been a very informative discussion on the significance of your work on mixed-layer instabilities.
You're very welcome. I'm glad I could provide some helpful insights. Please let me know if you have any other questions as you continue your research.